Welcome to this lecture on mathematical finance. Today, we are going to explore a fundamental concept known as the log-normal property of stock prices. If you have ever wondered how quantitative analysts and financial engineers model the unpredictable movements of the stock market, it all starts right here. We will build this concept from the ground up. So, let us dive in. Before we look at any math, let us think about how a stock price actually behaves in the real world. Imagine planting a tree in your backyard. That tree can theoretically grow infinitely tall over the years, but its height can never become a negative number. Stock prices behave exactly like this tree. Because of a legal concept called limited liability, your maximum loss is capped at exactly what you invested. A stock price can rise to infinity, but it can never drop below zero. Therefore, a standard symmetrical bell curve cannot accurately represent stock prices because it spills over into negative territory. This brings us to the log-normal property. Since we cannot use a normal distribution for the actual dollar prices, we need a different shape. The log-normal property formally states that the natural logarithm of a future stock price is normally distributed. The natural logarithm is simply a mathematical tool used to uncompound continuous growth. When we say a variable is log-normally distributed, we mean that if you take the natural logarithm of all its possible values, those new values will form a perfect bell curve. The actual stock prices form a lopsided curve that leans to the left and stretches far to the right. Let us visualize exactly what this means. On your screen, you can see a direct comparison between a normal distribution and a log-normal distribution. The blue curve represents the normal distribution. Notice how its left tail crosses the zero mark and extends into negative values. This makes it impossible to use for actual stock prices. Now look at the red curve, which represents the log-normal distribution. It hits a hard wall at zero. It never crosses into negative territory, and its right tail stretches out indefinitely. This perfectly models the reality of limited liability and unlimited upside potential in financial markets. Now that we understand the concept visually, let us look at its mathematical form. This formula is the cornerstone of the log-normal property. It explicitly states that the natural logarithm of the future stock price, denoted as S sub t, follows a normal distribution. The symbol script n stands for the normal distribution. Inside the parentheses, the first term is the mean, which is the natural log of today's price, S0, plus the expected return mu, minus half of the volatility sigma squared, all multiplied by time t. The second term is the variance, which is the volatility squared multiplied by time. When volatility increases, it actually drags down the expected growth rate. Let us see this formula in action with a concrete example. Suppose a stock is currently trading at $50. The expected return of the stock is 15% per year and its volatility is 20% per year. We want to find the mean and the variance of the natural logarithm of the stock price exactly 6 months from today. This will tell us the exact shape and location of the bell curve for the log prices. We start by writing down our given values and setting up the formula for the mean, which we will call M. Continuing with our calculation, we substitute our given numerical values into the mean formula. We plug in 50 for the initial price, 0.15 for the expected return, 0.20 for the volatility, and 0.5 for the half-year time period. First, we must square the volatility and divide it by 2 to find the volatility drag, which comes out to 0.02. We subtract this drag from the expected return of 0.15, giving an adjusted growth rate of 13%. Multiplying this by half a year gives 0.065. To finish finding the mean, we add that 0.065 to the natural logarithm of 50, which gives a final mean of 3.977. Next, we calculate the variance, which we will call V. The variance formula is simply the squared volatility multiplied by the time period. Squaring 0.20 gives 0.04. Multiplying by half a year gives a final variance of 0.02. This variance measures exactly how wide or spread out our bell curve will be over the 6-month period. Building on our previous calculations, let us find the 95% confidence interval for the actual stock price in 6 months. This means we want to find a lower price and an upper price such that we are 95% sure the stock will end up between those two numbers. Because the actual stock price is log-normally distributed, we must first find the confidence interval for the normally distributed log price. To do this, we need the standard deviation, which we will call D. We find D by taking the square root of the variance we just calculated, giving 0.141. Now that we have the standard deviation, we can calculate the lower bound L and the upper bound U of the log price. In a standard normal distribution, 95% of the data falls within 1.96 standard deviations of the mean. So, to find the lower boundary, we take our mean of 3.977 and subtract 1.96 times our standard deviation. This gives a lower log bound of 3.701. We do the exact same thing for the upper boundary, but we add instead of subtract, giving 4.253. We are now 95% confident that the log price will fall between 3.701 and 4.253. However, we need the actual dollar prices. To find these, we must reverse the natural logarithm by using the exponential function on both boundaries. Raising the mathematical constant e to the power of 3.701 gives us $40.49. Doing the same for the upper bound gives $70.32. Notice that this interval stretches further upward than downward, perfectly illustrating the right-skewed shape of the log-normal distribution. Now that we have successfully used the log-normal property formula, let us understand where it actually comes from. To prove this property mathematically, we must start with the standard model for stock price behavior, known as geometric Brownian motion. Geometric Brownian motion is a mathematical model that assumes a stock's percentage changes have a constant average growth rate and a constant level of random fluctuation. It breaks down the tiny, instantaneous change in the stock price into two separate parts, a predictable growth part and an unpredictable random part. This is the foundation of modern financial mathematics. This brings us to the mathematical representation of geometric Brownian motion. We express this continuous movement using a differential equation. In this equation, ds represents the tiny change in the stock price over a microscopic time step dt. The first term, mu times s times dt, is the predictable growth component, where mu is the expected return. The second term, sigma times s times dz, is the random shock component. Here, sigma represents the volatility and dz represents a random shock drawn from a normal distribution, acting like a coin flip that decides if the stock gets a random bump up or down. Let us begin deriving the log-normal property from this equation. Because we want to find the distribution of the natural logarithm of the stock price, we cannot just take the logarithm directly using standard algebra. Instead, we must use Ito's lemma, which is a special rule in stochastic calculus used to find the derivative of a function that contains random variables. When we apply Ito's lemma to the natural logarithm of the stock price, it tells us that the randomness actually drags the average growth rate down slightly. This reduction is the volatility drag we saw earlier in our formula. Moving forward with our derivation, we now have an equation for the tiny change in the natural logarithm of the stock price. To find the stock price at a specific future time t, we must add up all these tiny, instantaneous changes from today, which is time 0, up to time t. In calculus, adding up continuous changes is done through integration. Because the right side of our equation consists of constants multiplied by time and a sum of normal random variables, The result of this integration will inherently be a normally distributed random variable. This mathematical reality is what guarantees the shape of our final distribution. In this final step of our derivation, we look at the result of our integration. The difference between the future log price and today's log price follows a normal distribution. To isolate the natural logarithm of the future stock price, we simply move the logarithm of today's stock price to the right side of the equation. Since today's stock price is a known, fixed number, adding it to a normally distributed variable simply shifts the entire bell curve to the right or left without changing its fundamental shape. This gives us the final mathematical definition of the log-normal property, completing our proof. So, we have proven that the log-normal property holds. This brings us to why this matters in the real world of quantitative finance. This property forms the foundational assumption of the famous Black-Scholes option pricing model, which banks use every single day to price billions of dollars worth of financial derivatives. If financial models incorrectly assumed that stock prices were normally distributed, the models would assign a probability to the stock price dropping below zero. This would cause the models to spit out completely irrational prices, leading to massive financial losses and arbitrage opportunities. Let us summarize the key takeaways from this topic. First, because of limited liability, stock prices can never fall below zero, making standard normal distributions unsuitable for modeling actual prices. Second, the log-normal property dictates that the natural logarithm of a future stock price is normally distributed, creating a right-skewed curve for the dollar prices. Third, we saw how volatility inherently drags down long-term compounded returns. Understanding this mathematical framework is the essential first step before diving into advanced derivative pricing models, as it ensures our models respect the physical reality of the financial markets. You have now mastered the log-normal property.